most nights, Earth does not feel like a mystery. It feels steady in ways so ordinary that we almost stop noticing them. The air stays within a range a human body can bear. Water rises from the sea, gathers into cloud, and returns again as rain. The ground beneath us seems patient. The sky above us seems familiar. And the whole planet gives the impression of a world that simply knows how to continue. Dawn follows night. Seasons return. Life goes on. Because this continuity surrounds us from the beginning, it is easy to mistake it for inevitability. But the longer you sit with that impression, the stranger it becomes. This planet has remained habitable not for a few fortunate centuries, nor even for a few quiet geological ages, but across spans of time so immense that the mind resists them. During those ages, the sun changed, continents wandered, broke apart, and gathered again. The atmosphere did not remain this atmosphere. The oceans did not keep the same chemistry. Life itself altered the world. And yet, through all of that motion, Earth remained within reach of habitability. That is the quiet astonishment at the center of this story. Not simply that life exists here, but that the planet did not drift away from the conditions that made long life possible by any simple expectation. A world that changes this much ought, sooner or later, to lose its balance. It ought to freeze too far, or warm too far, or slip into a state from which surface life could not easily recover. But our planet seems to have done something subtler than remaining unchanged. It changed constantly, yet not without limit. It moved, yet somehow did not wander beyond return. Tonight, that is the mystery we are entering. We are not beginning with a broad survey of Earth systems, and we are not looking for a neat explanation that can be named once and filed away. We are beginning with a more unsettling question. Why has Earth stayed habitable for so long when, by all appearances, it should have had many chances to become unlivable? What kept this world within the narrow reach between sterile cold and sterile heat? What held water at the surface, chemistry in motion, and the possibility of life open across lengths of time that erase mountains, redraw seas, and make whole worlds of living things appear and disappear? At first, the answer seems as though it might be elegant. Then it becomes more complicated, then stranger, then humbler. What looks, from a distance, like simple planetary stability turns out to be something more like an ongoing negotiation between rock, air, water, heat, and eventually life itself. So before we reach the great cycles and the beautiful theories, we have to begin with a quieter reversal. We have to go back far enough that the gentleness of Earth no longer feels obvious. Earth should not have stayed gentle as easily as it did. If we travel far enough back into Earth's past, beyond forests, beyond animals, beyond any landscape that would feel recognizably ours, the world begins to lose the features that make it familiar. The continents are not yet the continents we know. The air is not the air we breathe. Whatever life may exist is nothing like the teeming surface life of later ages. It is natural. Then, to imagine the early Earth as simply hostile, too hot, too violent, too unstable for anything like enduring surface habitability. For a long time, that was close to the picture many people carried in their minds. A young planet still marked by the violence of formation, volcanic, battered, and largely unfit for anything gentle. But the evidence has complicated that image. Tiny zircon crystals, surviving from an almost unimaginably remote past. preserve chemical signatures that suggest liquid water may have existed on Earth's surface astonishingly early. They hint that the young Earth may not have been only a furnace or only a scene of violence. Somehow, even in that distant age, there may already have been rain, weathering, and surface water. That does not give us a simple picture of a mild, early world, but it does force us to imagine something unexpectedly gentle appearing much earlier than old intuitions would allow. That alone would make the young Earth feel more puzzling. But once that early evidence for liquid water is placed beside another fact, the mystery deepens sharply. The sun was weaker then. Over Earth's history, solar luminosity gradually increased. Billions of years ago, our star gave off less energy than it does now, not dim in a poetic sense, but dimmer in the energetic sense that matters for climate. By a straightforward reckoning, the early Earth should have been receiving less warmth than the Earth of today. And when those two ideas are held together, early surface water and a substantially fainter young sun, the familiar planet becomes difficult to explain. This is where the story stops being background and becomes paradox. If liquid water existed on the surface of the young Earth, while the sun was weaker, then some other part of the system must have been compensating. Something about the planet must have helped preserve warmth, reduce heat loss, or prevent a descent into long frozen silence. In that sense, Earth cannot have been acting like a passive stone, merely receiving whatever its star happened to provide. Even then, it begins to look less like an object and more like a system. That realization gives the faint young sun paradox its force. It is not only a scientific puzzle. A habitable planet under a weaker sun should not be a simple thing. And if that improbability appears very early, then perhaps Earth's long history of livability cannot be explained by luck alone. Perhaps the world possessed some way of resisting drift, some slow internal pattern that kept it from sliding too far toward frozen sterility or irreversible heat. Once that possibility enters the story, the Earth of the past begins to feel much less obvious than the Earth of the present. The problem is no longer just how life later flourished here. The deeper problem is how the stage remained available at all. How did the planet stay within range? How did it keep water at the surface? How did it move through enormous change without losing the basic possibility of habitability? A livable world begins to look less like a default condition and more like the result of repeated successful adjustments. Stability, seen this way, is no longer the absence of change. It is the ability to pass through change without breaking. So Section 1 leaves us with a young Earth that should have been colder than its watery surface suggests, and with the uneasy sense that our planet's habitability must have depended on something deeper than simple distance from the sun. The evidence does not yet tell us the whole answer, but it tells us where to look. And that is where one of the most beautiful ideas in Earth science enters the story. The first major answer does not arrive in the form of a rescue or a dramatic event. It arrives through rain falling on rock, chemistry working with immense patience across the surface of the planet, and the possibility that Earth has long possessed a thermostat of its own. The beauty of the first major answer lies in how little drama it seems to require. There is no grand intervention in it, no sudden correction, no moment when the world is snapped back into balance. Instead, the answer emerges from processes so slow and quiet that they can disappear almost completely from human attention. It begins with a simple thought. A planet does not need to control the sun in order to control how much of the sun's warmth it keeps. The atmosphere matters. Some gases trap heat more effectively than others, and among them, carbon dioxide has played a particularly important role in Earth's climate across deep time. If the early sun was dimmer, then one obvious possibility is that the early atmosphere held on to more heat than the present one does. But that only postpones the deeper question. If Earth has managed its temperature in this way across billions of years, what managed the carbon dioxide itself? Here, the surface of the planet starts to reveal itself as part of a slow, interlocking machine. Rainwater absorbs carbon dioxide from the air and becomes weakly acidic. When that rain falls on silicate rocks, it helps weather them. Those products are carried onward, often through rivers and eventually into the oceans, where carbon can be locked away in sediments and minerals. Meanwhile, Earth's interior is not silent. Through volcanism and related processes, carbon returns from deep reservoirs back into the atmosphere. It is not a quick cycle, and it is not tidy in the way small systems are tidy. But its power lies in feedback. If the planet becomes warmer, weathering tends to intensify. Over long timescales, more carbon dioxide is removed from the atmosphere, weakening greenhouse warming. If the planet becomes cooler, weathering slows. Carbon dioxide is then drawn down less efficiently, while volcanic inputs continue, allowing greenhouse conditions to build again, slowly, over geological time. This creates the possibility of something remarkable. A world that can partly steady its own climate through the exchange of carbon between sky, stone, say, and interior heat. For the mystery of the faint young sun, this is deeply satisfying. Under a dimmer young sun, a thicker greenhouse atmosphere could help preserve liquid water. Later, as the sun slowly brightened, long-term carbon drawdown through weathering could help keep the planet from overheating. The result is not perfect balance in every era, but a plausible long tendency toward correction. Earth begins to look as though it possesses a thermostat, not a mechanical one, but a geological and chemical one, built out of rain, rock, burial, and volcanic return. And what makes this answer especially appealing is that it changes the meaning of instability. Earth remains a restless world. Continents rise and erode. Volcanoes release gases. Oceans accumulate chemical memory. Nothing in this system is truly still. Yet that restlessness may be part of what allowed habitability to endure. A silent planet might not regulate itself nearly as well. In that sense, processes that seem destructive on a local scale begin to look protective on a planetary one. For a while, this feels almost sufficient. It explains why early Earth may have avoided deep freeze, and why later Earth may have avoided runaway heat as the sun brightened. It gives the planet a hidden regulating logic. But the more satisfying an answer becomes, the easier it is to notice its edges. Earth's history does not look like the history of a world gently moderated in every respect. Even within this larger stability, the planet still underwent vast transformations. The air did not remain quietly fixed. The surface did not merely sit beneath a geological thermostat and wait for life to decorate it. Something more complicated happened. Life arrived, and once it did, it began to alter the chemistry of the world itself. That is where the first beautiful answer begins to feel incomplete. Not wrong. Incomplete. The thermostat matters. The long carbon cycle matters. But if the question is why Earth stayed habitable for so long, geology alone may not be the whole story. The hidden system is widening. The planet is becoming stranger again, because the next turn in the mystery is this. Life did not simply emerge within a habitable Earth. In time, life entered the machinery and began to change the machine from within. Once that possibility appears, the whole atmosphere of the story shifts. Up to this point, Earth's long habitability can still be pictured as a largely geological balancing act, a patient exchange between rain, rock, ocean, and the deep interior. That picture remains essential, but it still treats life mostly as a beneficiary, a passenger protected by the larger system. The next turn asks us to imagine something much stranger. What if life was not only sheltered by Earth's stability, but gradually became part of what shaped that stability? This is one of the most unusual things about our planet when seen across deep time. Life did not arrive on a finished stage and simply begin performing. It altered the stage itself. It changed the chemistry of the air, the sea, and the surface. It did not merely adapt to the Earth it found. Over time, it helped create a different Earth from the one it inherited. At first, those changes were quiet. The early biosphere did not announce itself with forests, animals, or anything that would look dramatic to human eyes. It worked on smaller scales, in microbial worlds spread through ancient waters and along surfaces we can now only partly reconstruct. Yet small does not mean weak. Some of those early organisms were doing something with immense planetary consequences. They were using sunlight to split water and, in the process, releasing oxygen. From the perspective of the later Earth, oxygen can feel like the most ordinary thing in the world. It is the invisible condition large animals depend on from breath to breath. But on the early Earth, oxygen was not background. It was intrusion. At first, much of it did not remain free in the atmosphere. It reacted with surrounding materials, especially abundant reduced compounds in rocks and oceans. For long ages, the planet seems to have absorbed that new chemistry rather than allowing it to accumulate. And yet there are hints in the geological record that oxygen may have appeared in brief, partial whiffs before it became a durable feature of the atmosphere. That detail matters because it preserves the gradualness of the transition. The world did not simply flip from one state to another. It leaned, hesitated, and only later crossed a threshold. When that threshold was finally crossed, the consequences were profound. The Great Oxidation Event was not simply a gain. It was a remaking. A world with enduring atmospheric oxygen was a different planetary state from the one before it. New chemical pathways became possible. Older ones became difficult or impossible for some forms of life. This opened new futures. For others, it meant danger. What later ages would call a breathable atmosphere began, in part, as a disruption. That is why this section matters so much to the documentary's central question. It shows that Earth's habitability was not a matter of preserving one timeless set of conditions. The planet remained habitable partly by changing the terms of habitability itself. Life did not simply stabilize the world. It also destabilized older equilibria and pushed Earth toward new ones. The hidden system, which had seemed geological in its first beautiful form, now widens into something more entangled. Biology is no longer merely living inside the machinery. It has entered the machinery and begun to change how it works. This is also the moment when ideas associated with Gaia become suggestive, even if they are handled carefully. Their value is not that they offer a magical solution, but that they teach us to see the biosphere and the planet as inseparable in a deeper way. Life changes atmosphere. Atmosphere changes climate. Climate changes the conditions under which life continues. But that does not make the story simpler. In some ways, it makes it more unsettling. A planet partly shaped by life may be more resilient in certain respects, yet it may also become more capable of radical transition. Once again, Stability refuses to mean stillness. By now, the central question has changed in a subtle but important way. We are no longer asking only how Earth stayed warm enough or wet enough under a changing sun. We are asking how a planet remains habitable while the very presence of life transforms what that word can mean. And once that question is asked, long habitability becomes harder to imagine as smooth or guaranteed. That realization prepares us for the next turn. Even with geological feedbacks, even with life entering the machinery, Earth did not move through its history in calm equilibrium. There were moments when the system seems to have come frighteningly close to its own limits. If the earlier sections tempt us to imagine Earth as a world quietly correcting itself, this part of the story asks us to let go of that comfort. Feedbacks exist. Long-term regulation exists. The interaction of geology and life matters enormously, but none of that means the planet moved through time in a mild or evenly tempered way. One of the deepest lessons of Earth history is that stability can include episodes that, from a human perspective, feel almost unthinkable. There were times when the planet seems to have leaned toward near-global ice. The phrase snowball Earth carries a stark clarity. It suggests a world in which ice advanced far beyond the regions we now associate with it, perhaps reaching low latitudes, perhaps covering much of the planet in a frozen stillness severe enough to strain ordinary intuitions about habitability. The exact details remain debated. Some researchers imagine a harder, more thoroughly icebound world. Others see room for open water or scattered refuges where life could persist more easily. But even with those uncertainties, the larger implication remains powerful. Earth may have passed through conditions far more extreme than the present surface would ever suggest. That matters not simply because it is dramatic, but because it changes the meaning of long habitability. A planet can remain habitable across billions of years without being continuously gentle. The hidden system does not prevent all extremes. Sometimes it works by bringing the world back from them. Imagine the tempo of such a crisis. Not the sudden violence of a storm, but a slow planetary tightening. Ice reflects sunlight. Cooling encourages more cooling. The surface grows brighter, colder, harder to reverse. A feedback no longer toward balance, but away from it. In such a world, the image of Earth as a self-correcting thermostat begins to look incomplete. Some feedbacks stabilize, but others amplify. That is where the deeper continuity returns, even in a deeply frozen Earth. Some processes do not stop. Volcanoes do not simply fall silent because the surface is cold. Over long timescales, they can continue releasing carbon dioxide. If weathering has slowed dramatically under icy conditions, then that carbon is no longer removed as efficiently as before. Slowly, very slowly, greenhouse warming can rebuild. What looks at one moment like a plunge toward irretrievable cold may, over immense spans of time, become the setup for escape. This is the kind of answer Earth history gives again and again. Not rescue in the dramatic sense, but return through persistence. The planet does not remain livable because it avoids all danger. It remains livable because different parts of the system operate on different timescales, and those timescales can sometimes pull the world back from extremes that shorter views would mistake for endings. Seen this way, Snowball Earth is more than a case study in ancient climate. It corrects the story we might otherwise be tempted to tell. The hidden system that keeps Earth alive is not a smooth guardian maintaining a perfectly moderated world. It seems instead to allow deep excursions and, sometimes, recovery from them Habitability begins to look less like gentle balance and more like the preservation of return. That thought changes the central question again. Earlier, we asked how Earth stayed within range at all. Then we asked how geology and life together widened the machinery. Now we are forced to ask something harder. Was this endurance inevitable? Or did Earth remain habitable partly because, again and again, the interacting systems of rock, atmosphere, ocean, and life happened to stay within the broad reach of recovery? The question grows humbler because the record itself is humbling. A planet can have powerful stabilizing feedbacks and still come frighteningly close to states that seem hostile to surface flourishing. And once that possibility enters the story, the desire for a single elegant explanation begins to weaken. We are approaching the point where the documentary's question opens into its final shape. Not a solved riddle, but a more layered understanding. By this point, the original question has become larger than the version we began with. At first, it seemed that we were asking how Earth avoided freezing under a fainter sun, or how it prevented itself from overheating as solar brightness increased. Then the answer widened into long-term carbon cycling, into a geological thermostat built from weathering, burial, and volcanic return. After that, life entered the frame not as decoration, but as force, reshaping atmosphere and altering the conditions under which future life could exist. Then came the realization that even such a world could approach profound instability, and that long habitability might include episodes of near disaster. So what, finally, is the hidden system that keeps Earth alive? The most honest answer is that it does not seem to be one thing. It is not only the atmosphere, though atmospheric composition matters immensely. It is not only the carbon cycle, though without that long exchange, the climate story becomes much harder to understand. It is not only plate tectonics, though a restless planet capable of renewing surfaces and recycling interiors appears to matter deeply. It is not only life, though life transformed the planet and became entangled with its ongoing stability in ways that cannot simply be separated back out. The hidden system looks less like a device than a layered conversation across deep time, a set of feedbacks between rock, ocean, air, heat, and living things, each working at different speeds, each altering the others. That is already a profound answer, but it is not quite a final one. Because even a layered system of feedbacks may not account for everything, there remains, at the edge of the discussion, a quieter and more unsettling possibility that Earth's long habitability was not fully guaranteed, even by all the mechanisms we have described. Stabilizing feedbacks may be only part of the story. Contingency, the plain fact that certain paths were taken and others were not, may matter as well. In other words, Earth may have remained habitable not because the system made that outcome inevitable, but because the system, with all its powers of correction, also happened to pass through deep time without failing irreversibly. That possibility does not weaken the story. It deepens it. It means we are not looking at a planet whose survival was obvious from the start. We are looking at a world whose long livability may have depended both on remarkable regulatory tendencies and on the fact that those tendencies, again and again, proved sufficient, not perfect. Sufficient. There is something quietly moving in that distinction. A planet does not need flawless balance in every era to remain alive across billions of years. It only needs, again and again, not to fall beyond return. So the humbling answer is not that we have found the master switch. It is that the question teaches a different way of seeing, Earth is not stable because it is simple. It is stable, insofar as it has been stable, because complexity itself can generate resilience. Yet that resilience is neither infinite nor effortless. What looked at first like familiarity has become, by the end, a kind of improbability. The air around us, the water moving through the world, the temperate range in which forests grow and animals breathe. None of it feels quite as ordinary now as it did at the beginning. The planet remains beautiful, but no longer in the uncomplicated way of a background. It has become a survivor of its own deep history. And perhaps that is why this question matters beyond geology, beyond climate theory, beyond the ancient details of zircons, ice, oxygen, and stone. To ask why Earth stayed habitable for so long is really to ask what it means for anything living to persist in a changing world. At first, we are drawn to the grandeur of the timescale, to the almost overwhelming length of planetary history. But what lingers is something more intimate: stability, whether in a planet or in a life, is rarely the same thing as stillness. More often, it is the ability to absorb change, to pass through upheaval, to be altered without being entirely lost. Tonight we followed that idea down into deep time. We began with a planet that seemed ordinary, then found that its ordinary livability was anything but. We found an elegant answer in the long carbon cycle, then watched that answer widen as life entered the machinery and began changing the machine from within. We passed through frozen ages that showed how close Earth may have come to losing its balance. And we ended not with certainty, but with a more layered understanding. The hidden system that keeps Earth alive is real, but it is not simple. It is the world in motion, correcting, exchanging, shifting, enduring. And perhaps the most astonishing part of that story is not that Earth was perfectly designed to remain habitable, but that amid so much change, it remained within reach of life at all. So when the planet feels quiet again, it may be worth remembering that this calm has a very long history behind it. The gentleness of Earth is not shallow. It is deep, hard-won, and older than any human memory. For now, though, we can leave the question there, where it belongs, not fully closed, but widened. A familiar planet made strange, and then, in becoming strange, made more beautiful again. Good night.